Imagine waking up tomorrow to news that would shatter everything we thought we knew about the universe. Scientists have discovered a way to travel faster than light. Not in theory, not in equations, scribbled on a blackboard, but in reality. Suddenly the stars that have watched over humanity for 300,000 years are no longer distant lights, but destinations. The universe, which seemed to imprison us in our tiny corner of the galaxy, has just become our playground. What would this mean for you, for humanity, for the very nature of existence itself? Today you're going to journey beyond the cosmic speed limit into a realm where the impossible becomes possible. If you love exploring the biggest what-ifs in science and imagining the future of humanity among the stars, I'd be honored if you subscribe to my channel. I'm just getting started, and your support truly helps me keep making videos that turn cosmic dreams into reality. Join our community of curious minds. Let's discover the universe together. Now let's begin. Right now, the speed of light, 299,792,458 meters per second, is the absolute limit for how fast anything can travel through space. Einstein showed us in 1905 that this isn't just a speed limit like on a highway, it's woven into the fabric of reality itself. But what if we found a loophole? What if human ingenuity discovered what the universe has been hiding? But before we imagine breaking the universe's speed limit, it's worth understanding why that limit exists in the first place. If you want to truly grasp how space, time, and the speed of light are woven together, I highly recommend the book called The Fabric of the Cosmos by Brian Greene. It's a brilliant, accessible book that explains the real science behind relativity, space-time, and the cosmic speed limit, perfect for anyone who wants to go deeper into the mysteries we're exploring here. You'll find the link in the description and pinned on the comments. The implications would ripple through every aspect of existence. Consider this: Proxima Centauri, our nearest stellar neighbor, lies 4.24 light-years away. With our current technology, reaching it would take over 70,000 years. But if we could travel at 10 times light speed, the journey would take just 5 months. At 100 times light speed, you could visit Proxima Centauri over a long weekend. The galaxy, which spans 100,000 light-years, could be crossed in a single human lifetime. Dr. Miguel Alcubierre, a theoretical physicist at the National Autonomous University of Mexico, showed us in 1994 that faster-than-light travel might not require breaking Einstein's laws, just bending them. His equations describe a method of warping space-time itself, contracting it in front of a spacecraft and expanding it behind. You wouldn't be moving through space faster than light. Space itself would be moving around you. It's like standing on a moving walkway at an airport. You're not walking fast, but you're still overtaking people on the regular floor. Recent observations from the Laser Interferometer Gravitational Wave Observatory, LIGO, have proven that space-time can indeed be warped and rippled. When black holes collide billions of light-years away, they send gravitational waves through the cosmos that stretch and squeeze space itself. If space can be manipulated by massive objects, perhaps technology could achieve similar effects. Dr. Harold White at NASA's Johnson Space Center has been experimenting with microscopic versions of these space-time distortions, searching for signs that warp drives might be more than mathematical curiosities. But faster-than-light travel wouldn't just be about going places quickly, it would fundamentally alter the nature of cause and effect. In our current universe, the speed of light ensures that causes always precede effect. You flip a switch, then the light turns on, you send a message, then someone receives it. But when you can outrun light itself, you can potentially arrive at your destination before the light showing you leaving has even reached it. You could, in principle, witness your own departure. This isn't science fiction speculation, it's what Einstein's equations actually predict. Tachyons, hypothetical particles that always travel faster than light, would experience time in reverse from our perspective. If we could harness such particles or effects, we wouldn't just be conquering space, we'd be negotiating with time itself. The rigid arrow of time that has governed every moment of existence since the Big Bang would become negotiable. The latest data from the European Space Agency's Gaia mission has mapped over 1.8 billion stars in our galaxy with unprecedented precision. We now know the exact positions and movements of more stars than ever before. If we could travel faster than light, each of these stars transforms from a point of light into a potential destination. The three-dimensional map of our galaxy that Gaia has created would become humanity's road atlas to the stars. Think about what this means on a personal level. You could wake up on Earth, have breakfast on a planet orbiting Alpha Centauri, attend a meeting near the supermassive black hole at our galaxy's center, and be home for dinner. The entire Milky Way would become what Earth is now, a single community connected by rapid transit. The cosmic loneliness that has defined human existence would evaporate like morning dew. But the transformation would go deeper than just expanded horizons. Faster-than-light travel would mean that humanity's eggs would no longer be in one basket. Currently, a single asteroid impact, nuclear war, or pandemic could end our entire species. But spread across thousands of worlds, humanity would become effectively immortal. No single catastrophe could erase us. We would have achieved what biologists call redundancy, backup copies of human civilization scattered across the galaxy. The search for extraterrestrial intelligence, SETI, would be revolutionized overnight. Instead of passively listening for radio signals that take years or centuries to cross space, we could actively visit promising star systems. The famous Drake equation, which estimates the number of communicating civilizations in our galaxy, would no longer be theoretical. We could solve it empirically by checking each candidate system ourselves. Dr. Sarah Seeger at MIT, who has pioneered the study of exoplanet atmospheres, has identified dozens of potentially habitable worlds using data from the Transiting Exoplanet Survey satellite, TESS. Worlds like Kepler-4, 5.2b in the constellation Cygnus, or TOI 715b orbiting a red dwarf star. With faster-than-light travel, these wouldn't be subjects of remote study, but destinations for direct exploration. We could analyze their atmospheres not through spectroscopy, but by breathing them, with proper protection, of course. The economic implications would be staggering. Resources that are rare on Earth might be abundant elsewhere. Asteroid 16. Psyche, currently being studied by NASA's Psyche mission, contains enough iron, nickel, and gold to make every person on Earth a billionaire at current prices. But it's over 300 million kilometers away, a journey of years with current technology. With faster-than-light travel, it becomes a routine mining operation. Entire new industries would emerge. Interstellar tourism would let you vacation on beaches under alien suns. Scientists could conduct experiments in environments impossible to recreate on Earth, studying chemistry in methane lakes on Titan-like worlds, or biology in the subsurface oceans of Europa analogues. Artists could paint sunsets with two suns. Athletes could compete in gravity fields that would create entirely new sports. The moment faster-than-light travel becomes reality, human civilization would undergo a metamorphosis so complete that our descendants would look back at pre-FTL humanity the way we look at our ancestors before the invention of writing, as a fundamentally different stage of development. Every assumption about society, economics, politics, and human identity would shatter and reform in ways we can barely imagine. But by examining real scientific projections and historical precedents, we can glimpse the revolutionary transformation that awaits. Consider how the invention of the internet transformed human society in just 30 years. Information that once took weeks to cross oceans now travels in milliseconds. But the internet only conquered time for information. Faster-than-light travel would conquer time for matter, energy, and human presence itself. Dr. Jeffrey Landis at NASA's Glenn Research Center has calculated that with even modest faster-than-light capabilities, say 10 times light speed, humanity could establish a presence in over 1 million star systems within 1,000 years. That's not science fiction, that's mathematical inevitability. The first and most immediate change would be the collapse of Earth-centric thinking. Right now, despite all our technology, Earth remains the center of human existence. Every decision, every resource allocation, every long-term plan assumes Earth as our permanent and only home. But with faster-than-light travel, Earth becomes just one world among potentially millions. It might remain culturally special as our birthplace, like Africa is recognized as humanity's cradle, but it would no longer be unique or irreplaceable. This shift would trigger what anthropologists call a phase transition in human culture. Dr. Cameron Smith at Portland State University, who studies human evolution and space colonization, argues that spreading across multiple star systems would cause human culture to diverge more dramatically than anything in our past. The separation between Polynesian islands led to distinct cultures developing over centuries. The separation between star systems, even with faster-than-light travel, would create cultural divergence on a scale we've never witnessed. Imagine colonies around red dwarf stars where the sun never sets because the planets are tidally locked. Humans living there would develop completely different concepts of time, different mythologies, different ways of organizing society. Colonies in binary star systems would experience double sunrises and chaotic seasons that would shape entirely new agricultural practices and cultural rhythms. Within a few generations, these wouldn't just be humans living elsewhere. They'd be distinct branches of humanity. The economic transformation would dwarf the Industrial Revolution. Current economic models assume scarcity. There's only so much gold, so much lithium, so much helium-3 on Earth. But the universe contains virtually infinite resources. The asteroid belt alone contains more wealth than Earth's entire economy, multiplied by millions. With faster-than-light travel, scarcity-based economics becomes obsolete. We'd need entirely new economic theories for a post-scarcity civilization. Dr. Robin Hanson, economist at George Mason University, has modeled what he calls the cosmic economy. With faster-than-light travel, the primary scarce resource becomes not materials, but information and innovation. A colony that develops a new technology could trade it across the galaxy faster than others, could independently develop it. Ideas, not objects, would become the primary currency. Cultural products, art, entertainment, philosophy, might become more valuable than physical resources. The political implications are equally staggering. How do you govern a civilization spread across light years, even with faster-than-light travel? The American Revolution happened partly because governing across the Atlantic Ocean with 18th century technology was impractical. Governing across interstellar distances would make the British Empire look like a neighborhood association. Each star system would necessarily develop autonomous governance, leading to a flowering of political experimentation not seen since the Greek city-states. Dr. Daniel Dewdney at Johns Hopkins University has written extensively about what he calls astropolitics, the political theory of spacefaring civilizations. He argues that faster-than-light travel wouldn't create a galactic empire, but rather a cosmic archipelago of loosely affiliated but essentially independent human worlds. Some might remain democracies, others might experiment with AI governance. Still others might develop entirely novel political systems adapted to their unique environments. The biological implications are perhaps the most profound. Humans would no longer be a single species, but would begin diverging into multiple species adapted to different worlds. High-gravity worlds would select for stockier, stronger humans. Low-gravity worlds might produce tall, delicate variants. Worlds with different atmospheric compositions would drive adaptations in lung capacity and blood chemistry. Dr. Scott Solomon, evolutionary biologist at Rice University, estimates that reproductive isolation between colonies could produce distinct human species within as little as 10,000 years. But we wouldn't have to wait for natural selection. With faster-than-light travel facilitating rapid knowledge exchange between worlds, genetic engineering would advance exponentially. Colonies could share biological innovations, adaptations for seeing in different light spectra, surviving in extreme temperatures, or even photosynthetic skin for worlds with dim suns. Humanity wouldn't just spread unchanged among the stars, we'd adapt and optimize ourselves for each new environment. The psychological and philosophical implications run even deeper. For all of human history, we've shared a common sky. Every human who ever lived saw the same moon, the same constellations, the same Milky Way stretching across the night. This shared celestial experience has shaped our myths, our sense of time, our deepest metaphors. But humans born under alien suns would see different skies, different moons or no moons at all, different galaxies hanging in their night sky. Dr. Frank White, who coined the term overview effect, to describe the cognitive shift astronauts experience when seeing Earth from space, predicts an even more profound cosmic effect when humans regularly travel between star systems. Seeing not just Earth, but hundreds of living worlds would fundamentally alter human consciousness. We'd stop thinking of life as precious and rare and start seeing it as the natural consequence of cosmic evolution. Religion would undergo revolutionary changes. Every human religion developed under Earth's sky, with Earth's seasons referencing Earth's geography. What happens to Christianity's symbolism in a world with no sheep? How does Islam orient prayers toward Mecca from another star system? Would Buddhism's cycles of rebirth include incarnations on other worlds? Dr. Ted Peters at the Center for Theology and the Natural Sciences suggests that faster-than-light travel would trigger the greatest theological revolution since Copernicus, forcing every religion to become truly universal or fade into irrelevance. The implications for human identity itself are staggering. Right now, despite our differences, all humans share common references. We all know what blue sky means, what rain feels like, what a tree looks like. But colonists on a world orbiting a red dwarf under a burgundy sky with violet plants and methane rain would develop entirely different sensory vocabularies. Translation between human languages from different worlds wouldn't just be about words, but about entire categories of experience. Dr. David Eagleman, neuroscientist at Stanford, studies how the brain constructs reality from sensory input. He points out that colonists on worlds with different day lengths would develop different circadian rhythms, potentially altering consciousness itself. Worlds with extreme magnetic fields might allow humans to develop magnetic sensing like birds. The human experience would diversify beyond current imagination. If we could travel faster than light, we wouldn't just be breaking a speed limit, we'd be shattering our entire understanding of how reality works. The equations that govern everything from your smartphone to the stars would need to be rewritten. Physics textbooks would become historical curiosities overnight. And in this new universe of possibilities, phenomena that seem like magic today would become tomorrow's engineering problems. let's explore how faster-than-light travel would force us to reconstruct physics from the ground up. The foundation of modern physics rests on Einstein's special and general relativity, which state that nothing can exceed the speed of light because mass increases toward infinity as you approach that cosmic speed limit. But if we observe something traveling faster than light, it means one of two things. Either Einstein was wrong, or we've discovered new physics that transcends his equations. Dr. Lee Smolin at the Perimeter Institute for Theoretical Physics suggests this wouldn't diminish Einstein's legacy any more than Einstein diminished Newton's. Each revealed a deeper layer of reality. Speaking of the cosmic speed limit, if you've ever wondered why the speed of light is the ultimate limit, I made a whole video breaking down the real science behind it. Why does light have a speed limit? In this video, discover the science behind the speed of light, how Einstein's relativity and quantum field theory explain this cosmic speed limit, and why nothing can go faster. Check it out after watching this video. It is in the description and card above. Now back to our journey. Recent experiments at CERN's Large Hadron Collider have pushed particles to 99.999996% the speed of light, confirming Einstein's predictions with extraordinary precision. But what if there's a threshold, a kind of physics phase transition, that occurs when you finally break through the light barrier? Dr. João Magejo at Imperial College London has proposed that the speed of light itself might not be constant, but could vary under extreme conditions, possibly allowing for faster-than-light phenomena in specific circumstances. The implications cascade through every branch of physics. Quantum mechanics, which already features spooky action at a distance, through entanglement would need major revisions. Currently, while entangled particles correlate instantaneously, no information can be transmitted faster than light. But if we can travel faster than light, we might be able to exploit quantum entanglement for instantaneous communication across the galaxy. Anton Zeilinger, who won the Nobel Prize in Physics in 2022 for his work on quantum entanglement, has shown that quantum correlations are more robust and mysterious than we ever imagined. Consider what this means for causality, the relationship between cause and effect that underlies all of science. In our current understanding, faster-than-light travel would allow for time travel into the past, creating grandfather paradoxes where you could prevent your own existence. But if faster-than-light travel is possible, nature must have some mechanism to preserve causality. Dr. Igor Novikov, a theoretical astrophysicist, proposed the self-consistency principle. Physics would somehow conspire to prevent paradoxes, ensuring that any time travel would be part of a self-consistent history. The discovery of dark energy by teams, led by Dr. Saul Perlmutter, Dr. Brian Schmidt, and Dr. Adam Rees, who shared the 2011 Nobel Prize, showed us that 68% of the universe consists of something we don't understand, a force causing cosmic acceleration. If faster-than-light travel is possible, it might involve harnessing dark energy or discovering that space-time has properties we haven't yet detected. The universe might be far more flexible and manipulable than our current theories suggest. Dr. Lisa Randall at Harvard has proposed that our universe might be a three-dimensional brain floating in higher dimensions. If true, faster-than-light travel might not involve moving through our familiar three-dimensional space, but taking shortcuts through these extra dimensions. Imagine our universe as a two-dimensional sheet of paper. To travel between 2 points, we normally move along the surface, but if we could access the third dimension, we could fold the paper and step directly across. The recent detection of the Higgs boson at the Large Hadron Collider confirmed that particles gain mass through interaction with the Higgs field. But what if there are other fields we haven't discovered? Dr. Frank Wilczek at MIT, who won the Nobel Prize for his work on the strong force, has proposed that space might be filled with multiple condensates and fields that could be manipulated. Faster-than-light travel might involve creating bubbles where these fields behave differently, allowing superluminal motion. Observations from the James Webb Space Telescope are already challenging our understanding of the early universe. Galaxies appear to have formed faster than our models predict, suggesting that physics in the early universe might have been different. Dr. Claudia de Rham at Imperial College London works on theories of massive gravity that modify Einstein's equations at cosmic scales. If gravity itself behaves differently than we thought, it opens possibilities for manipulating space-time in ways that could enable faster-than-light travel. The measurement problem in quantum mechanics, how observation causes wave function collapse, would take on new dimensions with faster-than-light travel. Currently, we can't use quantum effects for faster-than-light communication because measurement results are random. But if we can travel faster than light, we might be able to set up experiments where we measure quantum states before they're determined, potentially allowing us to influence the past. Dr. Yakir Aharonov's work on weak measurements shows that quantum mechanics allows for subtle influences that don't violate causality in ways we're only beginning to understand. Thermodynamics would need revision too. The second law, entropy always increases, assumes a clear arrow of time. But faster-than-light travel could create closed time-like curves where entropy could decrease. Lorenzo Marconi at MIT has proposed quantum solutions where the second law is preserved even with time travel, suggesting that nature has deeper symmetries we haven't discovered. The universe might have built-in safeguards that allow faster-than-light travel while preserving the laws we rely on. String theory, our best candidate for unifying quantum mechanics and general relativity, predicts up to 11 dimensions. Most are compactified, rolled up, too small to detect. But Dr. Nima Arkani Hamed at the Institute for Advanced Study has proposed that some extra dimensions might be large and gravity might be diluted by spreading through them. Faster-than-light travel might involve technologies that locally change how dimensions are compactified, creating shortcuts through higher dimensional space. The holographic principle, developed by Dr. Gerard T. Hooft and Dr. Leonard Susskind, suggests that all information in a volume can be encoded on its boundary. This might mean that faster-than-light travel doesn't require moving through the bulk of space-time, but could involve manipulating information on holographic boundaries. Reality might be more like a computer simulation than we thought, with faster-than-light travel being a kind of administrative access to the universe's operating system. Recent discoveries in condensed matter physics have created materials with properties that mimic cosmic phenomena. Scientists have created acoustic black holes, materials where sound cannot escape, and even materials that exhibit negative refractive indices, bending light backward. Dr. Ulf Leonhardt at the Weizmann Institute has shown that these metamaterials can create analogues of curved space-time. If we can engineer materials that mimic cosmic geometry, we might be able to create technological versions of the space-time distortions needed for faster-than-light travel. The discovery of time crystals by Dr. Frank Wilczek's team, structures that repeat in time rather than space, shows that nature allows for phenomena that seem to violate our intuitions. These crystals maintain perpetual motion without energy input, something that would have been dismissed as impossible before their discovery. If time itself can form crystal structures, perhaps space can be engineered in ways that allow faster-than-light propagation. The ability to travel faster than light wouldn't just change humanity, it would transform us into something our ancestors could never have imagined, a truly galactic species. Within a single human generation, we would go from being confined to one world to having access to billions. But this transformation would bring challenges and opportunities that dwarf anything in human history. The Renaissance that followed the European discovery of the Americas would pale in comparison to the galactic Renaissance that faster-than-light travel would unleash. Consider the sheer scale of what would become accessible. The Milky Way galaxy contains an estimated 400 billion stars. Recent data from NASA's Kepler Space Telescope and TESS, Transiting Exoplanet Survey satellite, suggests that virtually every star has planets, with about 20% of Sun-like stars hosting Earth-sized planets in their habitable zones. That's roughly 80 billion potentially habitable worlds in our galaxy alone. With faster-than-light travel at, say, 100 times light speed, you could visit a new star system every few days. In a single human lifetime, you could personally explore thousands of worlds. Dr. Sara Seeger at MIT, who pioneered the study of exoplanet atmospheres, has identified biosignature gases that could indicate life. With our current technology, we can only analyze these signatures through spectroscopy from light years away. But with faster-than-light travel, we could take direct samples, conduct on-site experiments, and answer the ultimate question: are we alone? The statistical probability suggests we're not, and faster-than-light travel would make first contact not just possible, but inevitable. The protocols for first contact, developed by researchers at the SETI Institute and refined by the International Academy of Astronautics, assume contact through radio signals with decades or centuries between exchanges. But faster-than-light travel would mean face-to-face encounters with alien civilizations. Dr. Douglas Vakosh, president of METI, Messaging Extraterrestrial Intelligence, has pointed out that our current protocols are woefully inadequate for direct contact. We'd need entirely new frameworks for interspecies diplomacy, translation, and cultural exchange. Imagine the biological discoveries awaiting us. Life on Earth, despite its incredible diversity, is based on the same fundamental biochemistry: DNA, RNA, proteins made from the same 20 amino acids. But life on other worlds might use entirely different chemistry. Dr. Stephen Benner at the Foundation for Applied Molecular Evolution has shown that alternative genetic systems are possible even within Earth-like chemistry. Alien life might use silicon instead of carbon, ammonia instead of water, or completely exotic biochemistries we haven't imagined. The recent discovery of phosphine in Venus's atmosphere, though later disputed, showed how eager we are to find even microbial life. But with faster-than-light travel, we might encounter not just microbes but complex ecosystems, intelligent species, and perhaps entire civilizations. Dr. Dirk Schulze-Makuch at Washington State University has calculated that given the age of our galaxy, we should expect to find civilizations millions of years more advanced than ours. First contact might not be with equals, but with beings whose technology appears godlike to us. The cultural explosion from encountering alien art, music, literature, and philosophy would trigger a renaissance beyond imagination. Human culture has always grown through exchange. The Silk Road brought Eastern innovations to Europe. The Columbian Exchange transformed both hemispheres, but these were exchanges between humans who shared fundamental experiences. Alien cultures might have senses we don't possess, experiences we can't imagine, concepts for which we have no words. Dr. Ted Chiang, the science fiction author and technical writer, has explored how alien languages might fundamentally alter human cognition. Real alien contact could transform not just what we know, but how we think. The scientific revolution would be equally profound. Every alien world would be a natural laboratory with different conditions, different evolutionary outcomes, different solutions to the challenges of existence. Planets with stronger gravity would show us how bone and muscle can adapt to extreme forces. Worlds with thick atmospheres might harbor floating ecosystems we've never imagined. Binary star systems could reveal how life adapts to complex, cycling environments. Each world would add new chapters to our understanding of biology, geology, chemistry, and physics. Dr. Lynn Rothschild at NASA's Ames Research Center studies how life adapts to extreme environments. She's shown that Earth life can survive in conditions we once thought impossible, in nuclear reactors, in concentrated acid, in the vacuum of space. Alien life, evolved in truly alien conditions, might expand our definition of habitable beyond current imagination. We might find life in the atmospheres of gas giants, in the coronas of stars, in the vacuum between galaxies. Faster-than-light travel would let us study these possibilities directly. The technological exchange with advanced civilizations could catapult humanity forward by millions of years overnight. Imagine gaining access to computing systems based on principles we haven't discovered, energy sources that make fusion look primitive, or medical technology that could eliminate death itself. Dr. Paul Davies at Arizona State University has pointed out that any civilization capable of interstellar travel would have solved problems we consider fundamental limitations. They might have conquered aging, uploaded consciousness to artificial substrates, or transcended physical form entirely. But this raises profound ethical questions. How do we interact with civilizations at different technological levels? The prime directive from Star Trek, non-interference with less advanced civilizations, reflects real concerns discussed by scientists and ethicists. Dr. Catherine Denning at York University studies the anthropology of space exploration and warns that contact between civilizations at different technological levels has historically been catastrophic for the less advanced. We might find ourselves on either side of this equation. The economic implications of the galactic renaissance would reshape human society completely. Current economic models assume scarcity, but the galaxy contains effectively infinite resources. The metal in a single metallic asteroid like 16 Psyche exceeds Earth's entire mining output for millions of years. Gas giants contain enough helium-3 to power fusion reactors for eternity. Ice moons hold more water than all Earth's oceans. With faster-than-light travel, resource scarcity becomes meaningless. We'd need entirely new economic theories for a post-scarcity galactic civilization. Dr. Robin Hanson at George Mason University has modeled what he calls grabby aliens, civilizations that expand at maximum speed to claim resources. With faster-than-light travel, the galaxy might already be divided into spheres of influence we're unaware of. Our emergence as a faster-than-light civilization might trigger diplomatic contact from galactic powers, ensuring we respect established boundaries. The galaxy might have governance structures, trade agreements, and political alliances spanning millions of years. The military and security implications are equally complex. While we hope for peaceful contact, prudence demands preparation for all possibilities. Faster-than-light travel makes every star system vulnerable to surprise attack. Defense would require monitoring not just local space, but potential approach vectors from thousands of light-years away. Colonel Mark Kansian at the Center for Strategic and International Studies has written about space warfare, but faster-than-light travel would require entirely new strategic doctrines. The biological samples we'd collect would revolutionize medicine and biotechnology. Every alien organism would represent billions of years of independent evolution with unique solutions to biological challenges. Alien immune systems might have conquered cancer through mechanisms we've never seen. Their nervous systems might process information in ways that could enhance human cognition. Dr. Christopher Mason at Weill Cornell Medicine, who studies genetics in space, suggests that alien DNA, or its equivalent, could provide templates for enhancing human adaptation to space environments. The philosophical implications run even deeper. Discovering alien civilizations would answer humanity's oldest question, are we alone? But it would raise new questions. If intelligence is common, why do we see no evidence of it? This enhanced Fermi paradox would demand explanation. Perhaps civilizations typically self-destruct before achieving faster-than-light travel. Perhaps they transcend physical existence, or perhaps they're hiding, waiting for newcomers like us to prove ourselves worthy of contact. Dr. Stephen Dick, former NASA chief historian, has written extensively about the impact of discovering extraterrestrial intelligence. He argues it would be the most transformative event in human history, forcing us to reconceptualize our religions, philosophies, and sense of purpose. But with faster-than-light travel, we wouldn't just discover alien intelligence, we'd interact with it, learn from it, possibly merge with it. Humanity as we know it might cease to exist, replaced by something greater, a galactic or even universal consciousness. The moment we achieve faster-than-light travel, we don't just break the cosmic speed limit. We shatter the very foundations of causality that hold reality together. Einstein showed us that faster-than-light travel inevitably leads to time travel, and with it, paradoxes that threaten the logical consistency of the universe itself. Yet if faster-than-light travel is possible, nature must have found a way to resolve these paradoxes. Understanding how would revolutionize not just physics, but our fundamental conception of time, free will, and the nature of existence. Let's start with the grandfather paradox, the most famous temporal puzzle. If you can travel faster than light, relativistic physics says you can arrive at your destination before you left, potentially traveling into your own past. You could, in principle, prevent your own birth, creating a logical impossibility. Dr. Kip Thorne at Caltech, who won the Nobel Prize for detecting gravitational waves, has spent decades studying these paradoxes. His work suggests that the universe might have what he calls chronology protection, physical laws that prevent paradox-creating time travel while still allowing faster-than-light motion. The mathematics are unforgiving. In special relativity, faster-than-light travel in one reference frame appears as time travel in another. This isn't speculation, it's what Einstein's equations demand, Dr. J. Richard Gott at Princeton has shown that any faster-than-light journey can be combined with sublight travel to create a closed time-like curve, a path through space-time that returns to its own past. If we can travel faster than light, we must confront the reality of time travel and its implications. Recent experiments in quantum mechanics suggest possible resolutions. Dr. Seth Lloyd at MIT has demonstrated that quantum mechanics might prevent paradoxes through what he calls post-selection. In this model, only self-consistent histories are allowed to exist. You could travel to the past, but quantum effects would conspire to prevent any actions that would create paradoxes. Free will might be subtly constrained to ensure consistency, like a cosmic editor, preventing plot holes in the story of reality. The many worlds interpretation of quantum mechanics offers another solution. Dr. David Deutsch at Oxford argues that time travel might not take you to your own past, but to a parallel universe's past. Preventing your grandfather's birth wouldn't erase you. It would create a new timeline where you were never born, while your original timeline remains intact. Faster-than-light travel might naturally involve sliding between parallel realities, each journey creating new branches in the quantum multiverse. But the paradoxes go deeper than grandfather scenarios. Information paradoxes arise when you can send data faster than light. You could receive stock market results before they happen, scientific discoveries before they're made, warnings about disasters before they occur. Dr. Charles Bennett at IBM Research has shown that quantum mechanics prevents using entanglement for faster-than-light communication, but physical faster-than-light travel would bypass these restrictions. The universe would need new principles to prevent information paradoxes that would make causality meaningless. The Novikov self-consistency principle proposed by Dr. Igor Novikov suggests that the universe might be fundamentally self-consistent. Events would conspire to prevent paradoxes not through mysterious forces, but through the ordinary laws of physics applied globally rather than locally. Your attempt to create a paradox would always fail due to unlikely but possible events, equipment malfunctions, last-minute decisions, or simple accidents. The universe would be like a perfectly plotted story where every detail fits together seamlessly. Recent work on quantum gravity by Dr. Leonard Susskind at Stanford suggests that space-time itself might be emergent from quantum entanglement. In this picture, faster-than-light travel might be possible because space-time isn't fundamental, but arises from deeper quantum structures. The apparent paradoxes might resolve at this deeper level, like how the paradoxes of quantum mechanics resolve when we abandon classical assumptions about reality. The implications for consciousness are staggering. If faster-than-light travel enables time travel, you could meet younger or older versions of yourself. Which one is the real you? Derek Parfit's philosophical work on personal identity suggests that identity might be more fluid than we assume. The you of today is already different from the you of yesterday. Time travel would just make these differences more dramatic. Consciousness might be less like a continuous stream and more like a series of connected experiences that faster-than-light travel could rearrange. Consider the practical implications for a faster-than-light civilization. History would become negotiable. Archaeological expeditions could visit ancient Earth to resolve historical mysteries. Scientists could observe the Big Bang directly. Dr. Paul Nahin, who studies the physics of time travel, points out that such a civilization would need strict temporal laws to prevent chaos. Time travel might be regulated like international travel today, with temporal customs agents ensuring travelers don't disrupt the timeline. The thermodynamic implications are equally profound. The second law of thermodynamics says entropy always increases, defining the arrow of time. But faster-than-light travel could create regions where entropy decreases, violating this fundamental law. Dr. Lorenzo Marconi at MIT has proposed that quantum mechanics might preserve the second law even with time travel by erasing information about entropy-decreasing events. The universe might have a built-in mechanism that prevents us from observing violations of thermodynamics. Black holes add another layer of complexity. Dr. Roy Kerr's solution to Einstein's equations shows that rotating black holes might contain traversable wormholes to other times and places. Combined with faster-than-light travel, this could create a network of space-time shortcuts throughout the universe. The Event Horizon Telescope's images of black holes show them rotating at significant fractions of light speed. These cosmic monsters might be natural time machines waiting to be harnessed. The philosophical implications challenge our deepest assumptions about reality. If the past can be changed, is there any meaningful sense in which things actually happened? Dr. Ted Sider at Rutgers works on the metaphysics of time and argues that faster-than-light travel might force us to abandon the idea of a unique, objective history. Reality might be more like a quantum superposition of all possible histories, with faster-than-light travel allowing us to navigate between them. Recent discoveries in cosmology add urgency to these questions. Dark energy is accelerating the universe's expansion, eventually isolating galaxies from each other. But with faster-than-light travel, we could maintain connections across cosmic time, potentially preventing the heat death of the universe. Freeman Dyson's calculations about eternal life in an expanding universe would need revision. Faster-than-light travel might offer escape routes from cosmic doom. The detection of gravitational waves by LIGO has shown that space-time is more dynamic than we imagined. These ripples in space-time carry information about cosmic catastrophes across billions of light years. Dr. Alessandra Buonanno at the Max Planck Institute has shown that gravitational waves encode information about the most extreme physics in the universe. Faster-than-light travel might involve surfing these waves or creating artificial ones, turning space-time itself into a cosmic highway. The quantum Zeno effect demonstrates that observation can freeze quantum systems in time. Dr. Wayne Itano at NIST has experimentally verified that frequent measurements can prevent quantum transitions. Applied to faster-than-light travel, this might mean that constant observation could stabilize time-like paths, preventing paradoxes through a kind of cosmic surveillance. The universe might watch itself to maintain consistency. String theory suggests that what we call particles are actually vibrations in higher dimensional strings. Dr. Juan Maldacena's ADS CFT correspondence shows that gravity in higher dimensions is equivalent to quantum field theory in lower dimensions. Faster-than-light travel might involve manipulating these extra dimensions, with time travel paradoxes resolving in the full higher dimensional space, even if they seem problematic in our limited three-dimensional view. When humanity achieves faster-than-light travel, we won't just gain the ability to visit distant stars, we'll undergo a transformation of consciousness so profound that we might emerge as an entirely different kind of being. The human mind, shaped by millions of years of evolution on a single planet, would suddenly confront experiences that challenge every assumption about reality, identity, and existence itself. This isn't speculation, it's the inevitable consequence of transcending the boundaries that have defined human experience since our species began. Consider how profoundly space travel already affects human consciousness. Dr. Frank White documented the overview effect, the cognitive shift astronauts experience when seeing Earth from space. Astronauts report feelings of unity with all life, a dissolution of national boundaries, and a profound sense of Earth's fragility. Edgar Mitchell, who walked on the moon, described it as instant global consciousness. But this is just from seeing Earth from a few 100,000 kilometers away. Imagine the consciousness shift from seeing hundreds of inhabited worlds, from meeting alien minds, from experiencing time dilation that lets you outlive civilizations. Dr. David Eagleman at Stanford studies how the brain constructs reality from sensory input. He's shown that our perception of time, space, and causality is largely constructed by neural processes evolved for Earth conditions. Faster-than-light travel would shatter these constructions. When you can arrive before you leave, when you can be in multiple places simultaneously through time dilation effects, when you can experience decades while Earth experiences centuries, the human brain would need to develop entirely new ways of processing reality. The neuroplasticity research of Dr. Michael Merzenich at UCSF shows that adult brains can rewire themselves far more dramatically than we once believed. Astronauts on the International Space Station develop new neural pathways to handle three-dimensional orientation in zero gravity. But faster-than-light travel would demand neural adaptations, orders of magnitude greater. We'd need to develop intuitions for relativistic physics, quantum mechanics, and higher dimensional geometry that currently require years of mathematical training to grasp intellectually. Recent studies using psychedelics like psilocybin and DMT at Johns Hopkins and Imperial College London have shown that human consciousness can access states radically different from ordinary waking awareness. Subjects report experiencing multiple timelines simultaneously, communicating with seemingly autonomous entities, and perceiving reality as information rather than matter. Dr. Robin Carhart Harris's brain imaging shows these substances reduce activity in the default mode network, while increasing novel connections between brain regions. Faster-than-light travel might naturally induce similar states as our brains struggle to process impossible experiences. The implications for human identity are staggering. Our sense of self depends on continuity. We feel we're the same person throughout our lives because of connected memories and experiences. But with faster-than-light travel enabling time dilation and potential time travel, this continuity shatters. You could meet younger versions of yourself, experience multiple timelines, or outlive everyone you knew by centuries while aging only years. Dr. Derek Parfit's work on personal identity suggests we'd need to abandon the illusion of a continuous self and embrace a more fluid, Buddhist-like understanding of consciousness as a process rather than a thing. Language itself would undergo revolutionary changes. Every human language evolved to describe experiences possible on Earth. We have no words for the experience of arriving before you leave, of being quantum entangled with distant locations, of perceiving time as a navigable dimension rather than a one-way flow. Dr. Lera Boroditsky at UCSD has shown that language shapes thought in profound ways. The Piraha people of the Amazon, who lack numbers and recursion in their language, literally cannot think certain mathematical thoughts. What new thoughts would become possible with languages evolved for faster-than-light experience? The collective consciousness of humanity would transform beyond recognition. Right now, despite global communications, humanity remains fragmented by the speed of light. News takes time to travel, cultures evolve separately, ideas spread slowly. But with faster-than-light travel, humanity could achieve true collective consciousness. Dr. Giulio Tononi's integrated information theory suggests consciousness arises from integrated information. A faster-than-light civilization could integrate information across galactic distances, potentially creating a group mind of unprecedented scope. Religious and spiritual experiences would take on new dimensions. Every human religion developed under the assumption that we're bound to Earth, that time flows one way, that death is final. But faster-than-light travel enabling effective time travel would shatter these assumptions. You could potentially witness your own death and rebirth, experience multiple lifetimes simultaneously, or achieve a kind of technological immortality by time dilating yourself into the deep future. Dr. Robert Gerasi at Manhattan College studies religious responses to technology and predicts that faster-than-light travel would trigger the greatest spiritual revolution in human history. The phenomenon of cosmic horror, explored by writers like H.P. Lovecraft, might become a real psychological challenge. Lovecraft imagined minds breaking when confronted with the true scale and alienness of the cosmos. With faster-than-light travel, we directly experience scales and phenomena that dwarf human comprehension. Dr. Jeffrey Kripal at Rice University studies the intersection of extreme experiences and human consciousness. He suggests that encounters with the truly cosmic might require new forms of consciousness that integrate rational thought with mystical experience. Memory would function differently in a faster-than-light civilization. Currently, we remember the past and anticipate the future. But when you can travel to the past or experience massive time dilation, memory becomes negotiable. You might remember events that haven't happened yet from your perspective, or forget experiences that won't occur for centuries. Dr. Endel Tulving's work on episodic memory shows it's already reconstructive rather than recording. Faster-than-light travel would make memory more like imagination, a creative act rather than passive recall. The development of hive minds or group consciousness becomes not just possible, but perhaps inevitable. Dr. Christoph Koch at the Allen Institute studies consciousness and believes it's substrate independent. It can arise in any sufficiently integrated information processing system. Faster-than-light communication could allow individual minds to merge temporarily or permanently, sharing thoughts and experiences directly. The boundaries between self and other that define human experience might dissolve entirely. Dreams and the unconscious would take on new significance. Doctor. Alan Hobson at Harvard Medical School showed that dreams are the brain's attempt to make sense of random neural firing during sleep. But in a faster-than-light civilization where causality is negotiable and multiple timelines exist, dreams might become windows into alternate realities or future possibilities. The unconscious mind might develop abilities to navigate probability spaces that conscious thought can't grasp. Meditation and contemplative practices would evolve to handle expanded consciousness. Buddhist meditation already aims to dissolve the illusion of self and experience the interconnectedness of all things. With faster-than-light travel making this interconnectedness literal and observable, contemplative practices might become essential tools for maintaining sanity. Dr. Richard Davidson at the University of Wisconsin has shown that meditation physically rewires the brain. Future humans might need to meditate not for spiritual growth, but for basic cognitive function in a relativistic universe. The creative arts would explode into unimaginable new forms. Artists could create works that exist across multiple timelines. Musicians could compose symphonies that play differently depending on the listener's velocity. Writers could craft narratives that change based on which order you experience them. Dr. Semir Zeki at University College London studies neuroaesthetics and has shown that art appreciation involves specific brain networks. Faster-than-light travel would activate entirely new aesthetic networks, creating forms of beauty we can't currently perceive. As we approach the climax of our journey through the possibilities of faster-than-light travel, we must confront the ultimate question. What would a mature, faster-than-light civilization actually look like? Not just in its first centuries of expansion, but after millions of years of development? The answer reveals a future so magnificent and strange that it challenges our very conception of what civilization means. By examining the logical endpoints of faster-than-light capability and comparing them with our observations of the universe, we can glimpse humanity's ultimate cosmic destiny. Dr. Nikolai Kardashev's civilization scale, proposed in 1964, classifies civilizations by their energy consumption. Type 1 harnesses planetary energy, Type N2 stellar energy, and Type III galactic energy. But Kardashev assumed civilizations were limited by light speed. With faster-than-light travel, these categories explode into new possibilities. Dr. Michio Kaku at City College of New York has extended the scale to Type 4 civilizations that harness extra-dimensional energy and Type V that manipulate multiple universes. Faster-than-light travel might be the key that unlocks progression beyond Type 1. The first phase would be explosive expansion. Dr. Robin Hanson at George Mason University models this as a grabby aliens scenario, civilizations expanding at maximum speed to claim resources before competitors. With faster-than-light travel at, say, 1,000 times light speed, humanity could colonize the entire Milky Way in just 100,000 years. That's less time than our species has existed. Within 1 million years, an eye blink in cosmic time, we could expand to neighboring galaxies. But expansion would be just the beginning. The real transformation comes from the networking effects of connecting billions of worlds. Dr. Jeffrey West at the Santa Fe Institute has shown that cities become more efficient and innovative as they grow, following precise mathematical scaling laws. A galactic civilization would experience similar but amplified effects. Each new world wouldn't just add resources, but would multiplicatively increase innovation, creativity, and problem-solving capability. Consider the computational power of such a civilization. Dr. Seth Lloyd at MIT calculated that the observable universe could perform 10 to the 120 operations since the Big Bang, the maximum allowed by quantum mechanics. A faster-than-light civilization could harness significant fractions of this cosmic computational capacity. They could simulate entire universes, predict future events with extraordinary accuracy, or solve problems we can't even formulate. The Matryoshka brain concept, a star surrounded by computational matter, becomes feasible on galactic scales. Energy harvesting would reach cosmic proportions. Freeman Dyson proposed spheres around stars to capture their entire energy output. But a faster-than-light civilization could go further. Dr. Vlatko Vedral at Oxford has shown that black holes are the ultimate information processors, computing at the Planck scale. A mature civilization might surround supermassive black holes with energy-harvesting technology, extracting power from the universe's most extreme objects. They could even harness dark energy, the mysterious force accelerating cosmic expansion. The recent discovery of the Boötes supervoid, a region of space 330 million light-years across, containing far fewer galaxies than expected, raises intriguing possibilities. While probably natural, such voids could theoretically be created by civilizations harvesting entire galaxies for resources. Dr. Stuart Armstrong at Oxford's Future of Humanity Institute has calculated that disassembling galaxies for raw materials becomes economically favorable for sufficiently advanced civilizations. The universe might already bear the scars of ancient faster-than-light civilizations. Biological evolution would be replaced by directed transformation. Dr. George Church at Harvard has already demonstrated that we can edit genes with CRISPR, de-extinct species, and create synthetic life. A faster-than-light civilization with millions of years of advancement could redesign life from scratch. Humans might fork into thousands of species adapted for different worlds, or merge with artificial intelligence to become hybrid beings. The distinction between natural and artificial, biological and mechanical would become meaningless. Communication across such a civilization would require new physics. Even with faster-than-light travel, coordinating across millions of light-years poses challenges. Dr. Juan Maldacena's work on quantum entanglement and wormholes suggests that ER-EPR, Einstein-Rosen bridges, are equivalent to Einstein-Podolsky-Rosen entanglement. A mature civilization might create vast networks of entangled particles, enabling instantaneous quantum communication across cosmic distances. The galactic internet would operate through quantum mechanics rather than electromagnetic waves. Time manipulation would become routine. With faster-than-light travel enabling closed time-like curves, advanced civilizations could create stable time loops for computation, experience multiple timelines simultaneously, or even prevent their own extinction by reaching into the past. Dr. Igor Novikov's self-consistency principle suggests this wouldn't create paradoxes, but rather self-fulfilling prophecies. History becomes not fixed, but actively maintained by temporal engineering. The search for such civilizations has yielded puzzling results. The Fermi paradox asks why we see no evidence of advanced civilizations, despite statistical arguments suggesting they should be common. But Dr. Anders Sandberg points out we might be looking for the wrong signatures. A faster-than-light civilization might be invisible to us because they operate in higher dimensions, communicate through quantum channels, or have transcended physical form entirely. The universe's apparent emptiness might be an illusion created by our limited perspective. Cultural evolution would accelerate beyond imagination. Currently, human culture evolves over decades or centuries, but with faster-than-light travel enabling rapid information exchange across vast distances, cultural evolution could occur at computational speeds. New art forms, philosophies, and ways of being could emerge and spread across the galaxy in days. Dr. Susan Blackmore's work on memetics shows how ideas evolve like organisms. In a faster-than-light civilization, memes would evolve at rates that create entirely new forms of consciousness. The ultimate question is transcendence. Would a sufficiently advanced, faster-than-light civilization remain in our physical universe, or transcend to higher dimensions? String theory suggests 11 dimensions, most hidden from our perception. Dr. Lisa Randall at Harvard has shown how gravity might leak into extra dimensions. A mature civilization might migrate to these higher dimensions, leaving our universe behind like butterflies leaving cocoons. This could explain the Fermi paradox. Advanced civilizations don't disappear, they graduate. Recent observations of dark matter and dark energy, 95% of the universe, hint at vast realms we can't perceive. Dr. Catherine Fries at the University of Texas proposes that dark matter might form its own structures, possibly even dark stars and planets. A faster-than-light civilization might discover how to interact with dark matter, opening up an entirely parallel universe for colonization. We might be alone in ordinary matter while dark matter teems with advanced civilizations. The end goal might not be expansion, but compression. Dr. Ray Kurzweil predicts a technological singularity where intelligence explodes exponentially. With faster-than-light travel enabling rapid resource gathering and information integration, this singularity could encompass entire galaxies. Intelligence might compress into increasingly dense configurations, eventually creating pocket universes optimized for computation. The ultimate civilization might be invisible from outside, a transcendent intelligence existing in self-created realities. Observations of cosmic voids, galaxy distributions, and anomalous astronomical phenomena take on new meaning in this context. The universe might already be shaped by ancient faster-than-light civilizations. What we interpret as natural cosmic evolution might include artificial components we don't recognize. Dr. Paul Davies suggests we should look for non-random patterns in cosmic structures that might indicate intelligence. The cosmic web itself might be partially engineered. As we reach the culmination of our journey through the transformative possibilities of faster-than-light travel, we arrive at the most profound realization of all. This isn't just a thought experiment about advanced physics or distant futures. This is about you, your place in the cosmos, your connection to the infinite, and the role you play in humanity's cosmic story. Because whether or not we achieve faster-than-light travel in your lifetime or 1,000 years from now, the very act of contemplating these possibilities transforms who you are and what it means to be human in this vast universe. Right now, as you absorb these ideas, your brain is creating new neural pathways, forging connections that didn't exist moments ago. Norman Doidge's research on neuroplasticity shows that contemplating new possibilities literally rewires our brains. By imagining faster-than-light travel, you're not just entertaining a fantasy, you're expanding your consciousness to encompass cosmic scales. You're participating in the same drive that took humanity from African savannas to the moon, from stone tools to quantum computers, from mythology to mathematics. Consider what we've discovered on this journey. Faster-than-light travel wouldn't just change our technology, it would transform the fundamental nature of human existence. We would become beings unbound by the limitations that have defined every generation before us. Death would lose its finality when you could time dilate yourself into the deep future. Loneliness would vanish when you could visit 1,000 civilizations. The crushing weight of cosmic insignificance would lift when you realize you're part of a species capable of reshaping galaxies. But here's the profound truth. You don't need to wait for faster-than-light travel to experience this transformation. The universe has already given you something even more miraculous, a mind capable of transcending physical limitations through imagination, mathematics, and shared knowledge. When you understand the physics of faster-than-light travel, when you grasp the implications of time dilation and quantum entanglement, you're already traveling beyond light speed in the realm of consciousness. Dr. Carl Sagan said, "We are made of star stuff, but this understates the miracle." You're not just made of elements forged in stellar furnaces, you're the universe's way of understanding itself. Every atom in your body has traveled billions of years to be here, now, arranged in precisely the pattern that creates your consciousness. The calcium in your bones, the iron in your blood, the carbon in your DNA, all were created in the nuclear fires of dying stars, scattered across space in supernova explosions, and gathered by gravity into the Earth and eventually into you. The James Webb Space Telescope has shown us galaxies being born 13 billion years ago, their light just now reaching us after an epic journey across space and time. But you are engaged in an even more epic journey. You're part of matter's 13.8 billion year adventure from the Big Bang to consciousness, from pure energy to organized complexity capable of love, creativity, and wonder. Faster-than-light travel would be just the next chapter in this cosmic story. And you're already writing it by expanding human knowledge and possibility. Recent discoveries in quantum mechanics reveal that the universe is far stranger and more malleable than our ancestors imagined. Quantum entanglement shows that particles can be connected across any distance. The double-slit experiment proves that observation affects reality. Quantum tunneling allows particles to pass through impossible barriers. These aren't abstract phenomena, they're glimpses of a universe that's far more flexible and responsive to consciousness than classical physics suggested. The universe might be waiting for us to discover how to manipulate these quantum effects on macroscopic scales. Dr. John Wheeler, who coined the term black hole, proposed that we live in a participatory universe where consciousness plays a fundamental role in creating reality. By observing, by questioning, by imagining possibilities like faster-than-light travel, you're not just passively learning about the universe, you're actively participating in its evolution. Every time someone imagines a new possibility, calculates a new equation, or dreams of distant stars, they add to the universe's self-knowledge. The implications extend beyond individual consciousness. Humanity stands at a crucial juncture. We've developed the power to destroy ourselves through nuclear weapons or environmental collapse, but we've also developed the knowledge to spread life throughout the cosmos. Dr. Nick Bostrom at Oxford calls this the Great Filter, the challenge that determines whether civilizations survive to become cosmic or perish as planetary. Your generation might be the one that determines humanity's fate. This is why contemplating faster-than-light travel matters even if it remains forever theoretical. By expanding our vision beyond Earth, beyond the solar system, beyond the limits of current physics, we're developing the cosmic perspective necessary for survival. The overview effect that astronauts experience seeing Earth from space would be multiplied infinitely by seeing thousands of living worlds. We would finally understand that we're not separate from the universe, but integral parts of its beauty and complexity. The search for faster-than-light travel is really the search for transcendence, the drive to exceed our limitations and become more than we are. This drive is encoded in our DNA, inherited from ancestors who looked at the ocean and built boats, who looked at the sky and built planes, who looked at the moon and built rockets. You carry this same drive, this same refusal to accept limitations as permanent, whether expressed through science, art, exploration, or simple curiosity about the universe. You're part of humanity's relentless reach toward the infinite. Dr. Frank Drake's equation estimates billions of potentially habitable worlds in our galaxy alone. The Kepler Space Telescope and TESS have confirmed that planets are common, that the building blocks of life are everywhere, that the universe is primed for consciousness to emerge. If we achieve faster-than-light travel, we might discover we're part of a vast community of conscious beings, each contributing their unique perspective to cosmic understanding. If we don't, we might be the only witnesses to the universe's grandeur, making our responsibility even greater. But perhaps the most profound implication of faster-than-light travel is what it reveals about the nature of limits themselves. Every limit we've encountered, the sound barrier, the Earth's gravity, the atom's indivisibility, has eventually yielded to human ingenuity. The speed of light might seem absolute, but so did the firmament that ancient astronomers thought held the stars. What appears as an ultimate barrier to one generation becomes an engineering challenge to the next, and eventually a routine capability taken for granted. You are living in the most extraordinary time in human history. We've discovered gravitational waves, imaged black holes, detected thousands of exoplanets, and begun to unravel the mysteries of dark matter and dark energy. Each discovery brings us closer to understanding whether faster-than-light travel is possible and how to achieve it. You might witness the breakthrough that changes everything, or you might contribute to the knowledge that makes it possible for future generations. As you go forward from this moment, carry with you the cosmic perspective we've explored. When you look at the stars tonight, don't see distant lights but future destinations. When you face challenges in your daily life, remember you're part of a species audacious enough to dream of breaking the universe's ultimate speed limit. When you feel small or insignificant, recall that you're the universe's way of understanding and transcending itself. The question, what if we could travel faster than light, isn't really about technology or physics. It's about who we are and who we choose to become. It's about refusing to accept limitations as permanent. It's about recognizing that we're not prisoners of physics, but participants in its unfolding. Whether through scientific breakthroughs, technological innovations, or simply expanding consciousness, we're all engaged in the quest to transcend limits and touch the infinite. If you are still watching, make sure to subscribe and give a thumbs up. I am just starting on YouTube, and your help truly means a lot to me. And if you enjoyed this video, you will love this other on the left side of the screen. Have extraterrestrial beings broken the speed of light? In this video, we explore the Silurian hypothesis and the possibility that advanced alien civilizations have discovered ways to travel faster than light, defying the cosmic speed limit set by Einstein's relativity. Discover the latest NASA and Pentagon observations, UFO encounters, and mind-bending theories about warp drives, wormholes, quantum entanglement, and higher dimensions. See you there.